Hi guys, I will explain the moment of area, part 4, from equivalent shape to summary. I have a quiz for you. Here we have 4 kinds of rectangular shapes. What rectangle has the plus sense for product moment of area, IZY? I've explained the topics from the first moment of area to parallax theorem for rectangles, triangles, and circles. I will explain the principal axis in this video. The next 3 topics will be explained in the next videos. Let's look into the symmetric characteristics of the second and product moments of area. Upper 2 figures show mirror symmetry, and the lower 2 figures show point symmetry. In the case of mirror symmetry, the 2 cross-sections have the same second moment of area value, but the product moment of area values have the opposite signs. In the case of point symmetry, the 2 cross-sections have the same second moment of area value, and the same product moment of area value also. Pictures on the screen show the equivalent shapes for second moment of area. All the pictures from the first to the fourth have the same second moment of area because the first is symmetric with the second about the vertical axis, and the square shapes of the first are identical, and the triangle is symmetric with the fourth about the horizontal axis. The square shapes of 2 are identical, and the triangle is symmetric with the third about the horizontal axis. The fifth is not symmetric with all the others about any axis because the location of centroid of triangle is different from the other 4 shapes. Therefore, the fifth has different second moment of area from those of the other 4. The figures on the screen shows the equivalent shapes for the product moment of area. The product moments of area for the first and the second are the same, but that of the third is different from the other 2 because the first is point symmetric with the second about the origin, but not with the third. The third has different horizontal distance from the coordinate origin to the centroid of a triangle compared with the other 2. The product moment of area for the fourth and the fifth are the same, but that of sixth are different because the fourth is point symmetry with the fifth about the origin, but not with the sixth. The sixth is not point symmetric, but mirror symmetric with the fifth about the vertical axis. As a result, product moment of area of sixth has the opposite sense to that of the fifth. Consequently, the product moment of area of the sixth has different from the other 2. Can you roughly guess whether the value of the product moment of area is plus or minus by looking at the shape? I will explain that. The product moment of area for the white region of the number 1 and the number 2 pictures is 0 because they are mirror symmetric about both the vertical and the horizontal axis. The sense of remaining parts are minus in the picture 1 and plus in the picture 2. Therefore, the sense of product moment of area is minus in the picture 1 and the plus in the picture 2. We need to be careful at the sense of the product moment of area because the sense relies on directions of the axis. In the left picture, the positive z direction is to the left. Therefore, the sense of product moment of area is minus. On the other hand, in the right picture, the positive x direction is to the right. Therefore, the sense of product moment of area is plus. Sense of product moment of area is very important because the direction of principal axis relies on it. I will show you later in detail. Sometimes it is very confused on rotation angle theta. Is it per rotation of object or per coordinate system? Rotating an object theta degrees counterclockwise is equivalent to rotating the coordinate axis theta degrees clockwise. Let's consider an arbitrary coordinate system, z-y axis. Is it possible to calculate the second and the product moments of area for a coordinate system rotated by an arbitrary rotation angle theta prime? How can we easily calculate the second and the product moment of area for arbitrary rotations, theta prime, theta double prime, or theta triple prime, etc.? An easy way to do it is to use the principal axis and the Mohr circle. The principal axes are two axes orthogonal to each other, forming a set in which one second moment of area becomes the maximum about the 1/2 axis, and the other second moment of area is the minimum in the other axis. Then in all the other orthogonal coordinate systems passing through the same origin, the product moment of area becomes 0 about the principal axis. I will explain how to find the principal axis from arbitrary coordinate axis. In order to examine the relationship between the principal axis and the rotation of coordinate axis, let's consider how to calculate the second and product moments of area for the zy prime axis rotated clockwise by theta from the original axis zy coordinate system, assuming that we have already known the second and the product moments of area about the original coordinate system zy axis. If we can express the second and the product moments of area about the zy prime axis in terms of those about the zy axis, which have already known to us, we can easily calculate those about zy prime axis. The angle theta is defined as the y component divided by z component. Therefore, if the signs of both components are plus or minus, the sign of theta is plus, like this. It means clockwise. And if the signs of the two components are different to each other, like this, the sign of theta is minus, meaning counterclockwise, like this. This is very important because we find the principal axis with theta. If we interpret the sign of theta in the wrong way, we end up with the wrong principal axis. The coordinate components of a small area dA for the y prime axis can be expressed as the equation 1 in terms of components of the y-axis. Equation 1 can be written in the matrix form. Actually, this is the matrix for coordinate transformation. By the definition, The second and the product moment of area are defined as the equation 2. Therefore, substituting the equation 1 into the equation 2 for the corresponding terms, we can get the expression for the second and the product moments of area with respect to the zy prime axis in terms of variables in yz of the original yz axis. Among them, let's take the second moment of area, iz prime, as an example. Iz prime can be obtained by substituting y prime in the equation 1 into equation 2. Here we have three integral terms. The first one is second moment of area about the original z-axis, iz. The second one is second moment of area about the original y-axis, iy. And the last one is the product moment of area about the original zy axis. Therefore, we have the equation 3 for iz prime in terms of iz, iy, and izy, which are what we have already known. In the same way, we can get the equation 4 for the second moment of area, iy prime, and the equation 5 for the product moment of area, izy prime. Now, we can express all the second and the product moment of area for yz prime axis in terms of those of original axis yz coordinate system. The principal axis can be derived from the equation for the product moment of area. We know that the product moment of area equals 0 in the principal axis. Therefore, substituting 0 into the equation 5 for izy prime, we can get the angle theta from the reference axis to the principal axis. Theta is a directional angle, as I explained. The answer to the quiz is number 1. As you can see here, positive areas are larger and farther from the origin than the negative areas. Therefore, the sense of the entire area is positive. On the other hand, in number 2, the negative areas are larger and farther from the origin than the positive areas. Therefore, the sense of the entire area is negative. In number 3, the product moment of area is 0 because the cross-sectional shape is symmetrical about both of z and y axis. In number 4, the product moment of area is also 0 by the same reason of number 3. The cross-sectional shape is symmetrical about both of z and y axis. Here we have a summary. If two sections are mirror-symmetric, their second moment of area are the same. If two sections are point-symmetric, the second moment of area are the same, and the product moment of area are also the same. The principal axes are two axes orthogonal to each other, forming a set in which one second moment of area becomes maximum about one of two axes, and the other second moment of area becomes minimum in the other axis than in all the other orthogonal coordinate systems passing through the same origin. The product moment of area becomes 0 about the principal axis. The principal axis can be obtained using the fact that the product moment of area is 0 in the principal axis. When the positive direction of the reference axis are to be left and up, if the angle representing the principal axis is positive, the principal axis is in the clockwise direction from the reference axis, and if negative, the principal axis is in the counterclockwise direction. If you watch the previous videos, you can easily understand upcoming videos. In the previous video, E0042, I explained the second and product moment of area for rectangles and triangles. Recently, I explained the second product and the polar moment of area for a triangle and a circle. The next video will be conicity and plicity, part 17, moment of area, part 5. I will explain the principal axis and its angle from the reference axis. Please hit the thumbs up and catch the brand new videos by free subscription. So, what are you waiting for? See you in the next video. Goodbye, guys.